Hi, folks. It's Anton here from Chroma. Here to talk to you a little bit about embedding stores and vector databases and how they work in the context of LLM in the loop applications like the one you're building in this course. So by now, you've learned a little bit about embeddings and nearest neighbor and how to use them for similarity search. I want to talk to you a little bit about some of the software packages and tools available for you that will make that a bit easier, especially if you're working with large amounts of data or you're ready to build a production-grade application. So let's get right into it. What is an embedding store? An embedding store is basically a software package that abstracts away a lot of the operations that you've already learned about. So first, you take a set of documents that represent your knowledge base, and you can use the embedding store to embed them using its embedding function. And then when a query comes in, the same embedding function gets called. It generates an embedding as the query embedding, and then the embedding store itself performs the nearest neighbor search for you and returns the relevant documents to the LLM context window, thus basically simplifying a lot of the operations that you would have to implement yourself. So the next question is, when should you be using one? Well, the first answer is when your data gets sufficiently large. Computing distances to each embedding for each query is pretty slow and expensive, especially under certain distance functions. A good rule of thumb is that when you're over about 10,000 embeddings using some of the commercial or open source embedding models, it's probably a good time to switch to a vector database or embedding store, and we'll get to a little bit about why that is in a minute. The other important thing is not to underestimate the convenience that actually using an off-the-shelf package gives you here. LLM-powered applications need to support many users across many indices. You need to handle data and scaling automatically. And you want it to just work. So rather than getting into all the nitty-gritty implementation, as long as you understand what's going on, oftentimes it's easier to just use an off-the-shelf solution like Chroma. So how exactly do embedding stores and vector databases deal with large amounts of data without incurring the costs of computing distances between the query and every single embedding that it stores? Well, as we've seen, exact nearest neighbor basically requires us to scan over the entire list of embeddings and compute the distances to each one. That takes O(n) operations, commonly called linear time, where n is the number of embeddings you already have. Embedding stores typically use an approximate nearest neighbor algorithm. And basically what they do is they exploit the underlying structure of the data that you have stored, and they take only log n operations. In other words, they're sublinear. It's a lot less expensive to do an O log n lookup than it is to scan the entire list. And the way that they do that is because they trade recall. In other words, sometimes they might miss the truly nth nearest neighbor and grab something else in exchange for speed and computational complexity. Now, that might sound a little worrying, but the reality is that the trade-off between speed and recall can be tuned depending on the algorithm used, and there's a lot of flexibility in how these things are implemented. So going into a little bit more depth about approximate nearest neighbors. ANN algorithms are an active area of research, and there's a lot of different ones. Commonly used ones include things called inverted file indexes, locality-sensitive hashing, and hierarchical navigable small world graphs. And if you want to learn more details about each of these, there's plenty of detail available online. Different algorithms work best in different settings. A lot of the approximate nearest neighbor algorithms used in many solutions today are set up for the case where the index doesn't change very much and gets updated only infrequently. However, if we're building an LLM in the loop application, it's very likely that our data will mutate online quite frequently. And so a graph-based algorithm like HNSW works well in these types of applications because we can iteratively construct and iterate on the graph. So what's next? I mean, this all sounds great, but the issue is that there is quite a few fundamental limitations, even when you have a software package that's supporting you in finding nearest neighbors in this way, because it doesn't answer certain questions. It doesn't answer for you which embedding model is best for my task or your data. It doesn't tell you how you should be chunking up your data to ensure good results. And just because you've gotten the n nearest neighbors doesn't actually tell you whether those neighbors are relevant or how relevant they actually are. So what should you do with the information that they're not sometimes? And finally, I think it's really important, and one of the core principles of AI is that we can easily incorporate human feedback into the data that we're returning to the model. So providing opportunities for and affordances to actually do that for developers is something that's really important. These are all features that we're looking into building into Chroma. And as I said, this is a still growing, this is still a field with a lot of product experimentation going on. And we're hoping to support users like you in doing all of these things in the near future. Thank you.